So in this video we're going to be looking at the ionic product of water, Kw, and its calculations as well. Now when we look at pure water, right, pure water can actually ionize into H plus ions and OH minus ions. So let's say if I were to take 2 molecules of water, right, what will actually happen is that one lot of water will act as a Bronsted-Lowry acid and one lot will act as a Bronsted-Lowry base, and what we'd end up with is a H3O plus ion, and then we'd end up with an OH minus ion as well. Now if I were to cancel off water from either side of this equation, so I remove water over here, get rid of that, I remove water over here and I get rid of that, and I'm now left with H plus, right, we can see that we've actually formed a simplified equation to show how water is in equilibrium itself, right? Now in terms of equilibrium, we know that we can actually work out a value for the equilibrium constant, but if we were to look into it a bit deeper, right, and look at the concentration of water, the concentration of water is a constant value because the equilibrium is going to lie very far to the left hand side, and so, right, if that's the case, right, hardly any of water actually ionizes. This ionization process only happens a tiny bit, and so if we were to simplify this a bit further, we can move this lot of water to the left hand side over here, and that gives us this equation over here. Now because we've got two constants next to each other, remember the concentration of water is going to be a constant, Kc is a constant, we can actually create a new constant, and that new constant is going to be known as Kw, and we call that the ionic product of water. And so this is the equation that we need to be able to remember, right? Now one thing that you might notice here as well is that you've been given the concentration of H plus over here, which you can actually use to find the pH of, let's say, pure water, for example, and then you've also got the concentration of OH minus ions as well, which you can use when dealing with bases and stuff. So let's say if I were to look at the ionic product of water, right, one fact that we have to remember is that at 25 degrees, or unless it's not specified, is that Kw is going to be equal to 1 times 10 to the power of minus 14, and just like other things like Kc, Kp and Ka, it's going to be temperature dependent as well. So moving on, right, why do we actually use the ionic product of water? Well, we can actually use this to calculate, first of all, the pH of pure water itself, and we can also use it to calculate the pH of strong bases as well. And we need to be able to use the following assumption when dealing with pure water, and that is that the concentration of H plus is going to be equal to the concentration of OH minus, because again the equilibrium lies so far to the left, because hardly any water ionizes, you end up with lots of unionized water itself. So yeah, if that's the case, right, you can actually rearrange that and you can make a new equation which looks like this, where you can actually calculate Kw, or you can actually calculate the H plus concentration of pure water and then find pH as well. So yeah, right, we already know and we've already established that Kw at 25 degrees Celsius is going to have a value of 1 times 10 to the power of minus 14, and this is also given on your data sheet. And you also need to remember a temperature of 298 Kelvin, because that could also be used as well. Now looking at an example over here, we're asked to calculate the pH of water at 373 Kelvin if Kw at this temperature is going to be 51.3 times 10 to the power of minus 14 mole to dm minus 6. So if we were to look at this example over here, right, they've actually given us a temperature and they've actually given us a value for Kw. Now if we look at our equation, right, we've got Kw, and that is going to be equal to the concentration of H plus times by the concentration of OH minus. Now because we're dealing with pure water over here, right, we can actually use the following assumption to make the concentrations of H plus and OH minus equal. So I know that the concentration of H plus squared is going to give me my value of Kw. If that's the case, right, I can rearrange this now to make the concentration of H plus a subject, and what I actually end up with is the concentration of H plus being equal to the square root of whatever Kw is actually going to be, right? And so if that's the case, right, I know my value of Kw, that's going to be 51.3 times 10 to the power of minus 14, and so if I were to put that in my calculator, what I actually end up with is a value of 7.16 times 10 to the power of minus 7, and that's going to be in mole per decimeter cubed. And then to find pH, right, all I'm going to do is minus the log of that value, and so I'm going to do minus the log of 7.16 times 10 to the power of minus 7. I'll put that in my calculator, and what I end up with is a value for pH is 6.15, right? So there I get my mark over here for actually using the KW equation and the approximation, a mark over here, right, for actually calculating the value for the concentration of H plus, and then another mark over here for calculating the pH of water itself, right? So yeah, if we were to move on, I've got 3 examples that I want you to have a go at. Pause the video and then resume once you're ready to move on. So before I attempt any of these, I'm going to think about the expression for Kw, which is going to be the concentration of H plus times by the concentration of OH minus. And then I'm going to simplify this a bit further, where I look at Kw, right, but when we're dealing with pure water. When we deal with pure water, this equation now becomes the concentration of H plus squared, because the concentration of OH minus is now equal to the concentration of H plus itself. And so let's say if we're asked to calculate the pH of water at 60 degrees Celsius, if Kw at this temperature is going to be 9.31 times 10 to the power minus 14, I know that I need to calculate a concentration of H plus before I calculate pH, and that concentration of H plus is going to be equal to the square root of Kw, which is going to be the square root of 9.31 times 10 to the power of minus 14. I do that, I put it in my calculator, and I end up with a value of 3.05 times 10 to the power of minus 7, and that's going to be in moles per decimeter cubed. And then what I can do is work out a value for pH by doing minus log of the concentration, and so in that case it's going to be 3.05 times 10 to the power of minus 7, and I end up with a value in my calculator as being 6.52. So again, there's my final answer for the pH to 2 decimal places. What about the next one? We're asked to calculate the pH of pure water at 25 degrees Celsius. Now remember, if we're given 25 degrees Celsius or 298 Kelvin, we know that Kw at this temperature is going to equal 1 times 10 to the power of minus 14. If that is the case, right, we can find the concentration of H plus, just as we did before, by doing the square root of Kw, which is going to be 1 times by 10 to the power of minus 14. We do that, we put in our calculator, and what we end up with is a value of 1 times 10 to the power of minus 7, and that's going to be again in moles per decimeter cubed. And so to find pH, all I'm going to do is do the minus log of that value, so I end up with the following, and my final answer being a pH of 7.00. What about the next one? Well, we're asked to calculate the concentrations of H plus and OH minus in a solution with pH being equal to 7 at 25 degrees Celsius. So again, we know that our value for Kw is going to be 1 times 10 to the power of minus 14. And we know that we can calculate H plus from this actual pH itself. So I need to do concentration of H plus is equal to 10 to the minus pH, which in this case is going to equal 10 to the minus 7. And so what I end up with is a value of 1 times 10 to the power of minus 7. And again, that's going to be in mole per decimeter cubed. Now I found the concentration of H plus in this instance. I know my value for Kw, right? And in this case, right, I've got one of my answers over here. That's the concentration of H plus. To find the concentration of OH minus, right, I've got to think back to this equation over here. How can I be sure about the concentration of OH minus? Well, I need to be able to rearrange this, so I end up with the concentration of OH minus being the subject, and then that is going to be equal to Kw divided by the concentration of H plus, and then that's going to be equal to 1 times 10 to the power of minus 14 divided by 1 times 10 to the power of minus 7. I'll put that in my calculator, and what I end up with is a value of 1 times 10 to the power of minus 7 as well, and that's going to be in moles per decimeter cubed itself, right? And so I've now worked out a value for the concentration of OH minus ions there as well.